Hey guys, in this video I want to talk about continuity and differentiability. So these are two very fancy sounding words that simply describe a function at a given point. So I want to start with continuity. So a function f, just any function that I'm calling f, at an arbitrary point a is continuous if this holds true. So it looks very complicated, but it's really not that bad. So all this says is the limit of f from the left side of point A and the right side of point A have to meet up, have to be the same, they have to be equal. So whenever you're looking for continuity or differentiability, you're going to be interested in a particular point on a function, and I'm calling that point A. So what I'm going to do to test this first equal sign is, if the limit of f at A is equal from the left and right side, my fingers are going to meet at point A when I trace them on the graph. So let me show you what that means. So I have an example here of discontinuity, and it is a vertical asymptote. So here this function f has a vertical asymptote at x equals -2. So I'm going to say my point of interest is -2, so A equals -2. So to test if the limit of f from the left side and the right side of -2 are equal, I see if my fingers meet at that point. So I'm going to trace the graph from the left and the right side of A, which is -2, and my fingers don't meet, right? They go in opposite directions. So this equal sign is not true. This rule is violated. And also, this value here, these two have to equal each other, but they also have to equal the value of the function at point A. This function is actually undefined at A, right? At A equals -2, at x equals -2, there's no value here. It's just an asymptote. So for more than one reason, a vertical asymptote is an example of discontinuity, or a discontinuous point in this function. Okay, another common example you run into is a hole. So a hole, it looks exactly like this. You know, you'll have a function that goes on and it looks continuous, and then suddenly there's just a gap in the function. And then it continues off right where it left off, and we call that a hole. So let's run our test here. And at this point, I'm going to say there's a hole at x equals 3, so A is 3. That's our point of interest. So to test if the limit of f as x approaches A from the negative side and the limit of f as x approaches A from the positive side are equal, I trace my fingers and make sure they meet. So from the left side of x equals 3, or A equals 3, and the right side of A equals 3, my fingers do meet, right? So this first equal sign is true. So that rule, that criteria is met. But we also have to make sure that this value here, and look, it turns out to be 2, right? That's where they meet at y equals 2. Is that equal to the value of f at point A? Well, look, we have a hole. So the value of this function at 3 is not defined. So this rule is broken. So that's why a hole is an example of a discontinuity. All right, one last example, jump discontinuities. You'll see these pretty frequently. So let's run our test here. So first of all, our point A is going to be 0. That's our point of interest. So is the limit from the left side equal to the limit from the right side? So at point 0, let me trace in here. Nope, my fingers don't meet. So this rule is automatically violated. So even though we have a defined value at f of A, so f of A here would be just 0, this rule is broken. So therefore, these are all examples of discontinuities. Okay, moving on to differentiability. So a function f at point A, an arbitrary point A, is differentiable if this holds true, okay? And so this says something very similar to what we set up here, but notice instead of f, I have an f prime. And f prime simply means the derivative function of f. So this says the limit of the derivative function at our point of interest A has to be equal from the left and right side, and that also has to be equal to the value of the derivative function at point A. And another way to rewrite these two terms is like this, using the actual definition of the derivative. So another way you could rewrite this entire rule is you could say this has to equal this, has to equal this. So make sure you know that these two are the same and these two are the same. So for differentiability, and specifically examples of non-differentiability, it's important that you can recognize these points graphically. So you need to be able to look at a graph and point out just visibly what is non-differentiable. So one example is where you see the slope is perfectly vertical. So whenever the slope is vertical, it's undefined, right? So that's what a derivative means. If you differentiate something, you're finding its slope. So we can't possibly differentiate something if the slope is undefined. So whenever you see a point like this where the slope looks truly vertical, so at x equals 0 here or at a equals 0, this would be a point of non-differentiability. Other examples of non-differentiability are corners, or sometimes called sharp points in a graph. So this is like a corner or a sharp point, and then you'll see cusps. This is kind of a cusp where it kind of curves up into a point and then curves back down. These are two more examples of non-differentiability. And if you had the actual function here, you could probably make use of this rule, but usually for differentiability, it's more important that you can just look at the graph and see, okay, if I've got a sharp point or a corner or a cusp or a vertical line, those are all examples of non-differentiability. And finally, I'd like to point out an important rule, and that is that all differentiable functions are continuous, but not all continuous functions are differentiable. So what that means is that, for example, if I know a function is differentiable at point A, that means it has to be continuous at point A. But just because a function is continuous at point A, that doesn't mean it's differentiable at point A. So keep that in mind. Okay, I'd now like to move on to an example problem. So suppose all of these things in the blue boxes are true. Suppose we have all of that information. They ask, part A, is f continuous and or differentiable at x equals 1? So first let's check continuity. So to do our continuity check, we're going to use our rule. We're going to say, is the limit of this function f equal from the left and right sides of our point of interest? And they told us from the left side, the limit of f was equal to 3 from our point of interest of 1. So this is 3. And they told us this was also 3. So from the right side of 1, our limit of f is also 3. And then also f of 1, our point of interest, is 3. So they all equal each other. So this function is continuous at x equals 1. Now let's do a differentiability check. So again, we know our differentiability rule can be written in this form, and that's convenient because that's what they gave us, right? So to test our point A, or x equals 1, or a equals 1, we'll put in a, or 1, here and here, right? Here and here. And we know to test from the left and right sides for that limit, we do h goes to 0 from the negative side, and h approaches 0 from the positive side. So this tests the continuity of the derivative function to see if it's differentiable. So we see, is the limit as h approaches 0 from the negative side of the definition of the derivative at point a is 1, is that equal to the same from the right side? Well, they told us this was 2 and this was 0. So 2 does not equal 0, right? So we know the function is not differentiable at x equals 1 or at a equals 1. And now they want us to sketch a possible graph of this function. So what you do for this is you look at the information you were given, and what I started with is the low-hanging fruit. They told me f of 1 was equal to 3. So I started out, I drew my axes, my y-axis and my x-axis, and I knew f of 1, so at x equals 1, y equals 3. So I knew that point was going to be here, right? And then I used these two pieces of information to finish the graph. So this function, this expression says that from the left side of x equals 1, the slope is 2, right? This says as you approach the differentiability check from the left side, the slope is 2. So what I did is I counted up 1, 2, 1. Rise is 2, run is 1. So the slope is 2 leading up to x equals 1. And this means that the slope is equal to 0 past 1, or approaching 1 from the right side, right? Because this is the definition of the derivative for f, right? At a equals 1 from the right side. So that means that this slope is 0, and from approaching x equals 1 from the negative side, the slope must have been 2. So I hope that makes sense. If you'd like to hire me as your custom tutor, please contact me at facebook.com/denovotutoring, and I'll see you guys in the next video. Thanks a lot.